This is the second video of the playlist Acid-Base Balance. In this video tutorial, I am going to discuss about buffer mechanism for the regulation of pH. So let's first look at what is buffer. Chemically speaking, a buffer is a mixture of weak acid and its strong conjugate base. Or it may be reverse. It may be a combination or mixture of weak base and its strong conjugate acid. Now let's try to understand this concept by taking one example of a mixture of weak acid and its strong conjugate base. So this Ha is the general representation of acid, and in this case it is weak acid. As this Ha is weak acid, it is undergoing only partial dissociation into H plus and A minus. This partial dissociation, it is shown by this reversible arrow. So Ha is currently at the equilibrium with H plus and A minus. Now whenever any dissociation is at the equilibrium, we can always define its equilibrium constant, which is some constant number. So for this particular system, equilibrium constant is equal to the molar concentration, the product of molar concentration of this right side reactant divided by product of molar concentration of left side reactant. Right? So we can write mathematically that this Keq, that is equilibrium constant, is equal to molar concentration of H plus into molar concentration of A minus divided by molar concentration of Ha. Remember, here Ha is the weak acid and this A minus is the conjugate base. Right? Now as this equilibrium constant Keq, it is specific for this weak acid. So instead of this subscript Eq, I can write subscript A to specify that we are talking about acid. So Keq here in case of weak acid, it is represented by Ka. Now we are more interested in this H plus ion concentration. So let's rearrange this formula to isolate this H plus concentration on one side and remaining everything on other side. So after rearrangement, we can get H plus is equal to Ka into Ha divided by A minus. Now let's take log on both the side. So logarithm of H plus is equal to logarithm of Ka plus logarithm of Ha divided by A minus. Now we know that negative log of H plus is the pH. Here it is positive. So we need a negative sign over here. So let's take a negative sign on both the side of this equal sign. So we get negative log of H plus is equal to negative log of Ka minus log of Ha divided by A minus. We know that negative logarithm of H plus, it is the pH, and similarly defined word is the pK, that is negative log of Ka. Now we can remove this negative sign and convert it into positive sign by just taking inverse of this division. Let's apply all these three changes into this formula. So we derived that pH is equal to pK. Remember, pK is the negative log of Ka, and plus log of A minus divided by Ha, that is inverse of this. So I am making positive sign over here. This formula is very important whenever we discuss about buffer, and this formula popularly known as Henderson-Hasselbalch equation. Right? Now we should not forget that this A minus over here, it is a conjugate base, and this Ha, it is the weak acid. So instead of writing as A minus and Ha, we can also represent this Henderson-Hasselbalch equation like literally spelling out, that is pH is equal to pK plus log of conjugate base divided by acid. So we had seen the chemical nature of buffer, but what about functionality? So functionally speaking, buffer resists changes in the pH of solution that contains it. It will mitigate any change in the pH. Okay. So buffers are very important for the maintenance of pH. Here I would like to specify one word, that is known as buffering capacity. Buffering capacity, its literal meaning is taken that it is the ability of a buffer to resist the changes in the pH. Now buffering capacity, it is determined or dependent on two factors. The first factor is that buffering capacity is maximum when pH of solution is pKa plus or minus 1. For example, if you consider bicarbonate buffer system, its pKa value is 6.1. Now that means it is most effective buffer between the range of 5.1 to 7.1 pH, right? So buffering capacity is maximum when pH of a solution is pKa plus or minus 1. The second important determinant factor is the concentration of buffer. So buffering capacity increases with the amount of buffer present in the system. Suppose you have two buffer. One buffer is 0.1 molar bicarbonate buffer and other buffer is the 0.2 molar bicarbonate buffer. So here concentration of buffer is more. So this buffer will be more effective than this. If we have 0.3 molar bicarbonate buffer, then 0.3 molar will be more effective than this 0.2 molar buffer, right? So we see that buffering capacity, it is determined by two factors. One is the pKa and second one is the amount of buffer present in the system or concentration of buffer which is present in the system. Now let's see what are the major buffers in different body fluids. So we cannot talk about all the body fluids, but majorly we can talk about these four body fluids. The first one is extracellular fluid, then blood, then intracellular fluid, and then urine. If we talk about extracellular fluid, here three buffers are very important. The first one is bicarbonate buffer, which is the most effective buffer in ECF. Then on the second rank, there is a protein as a buffer. And on the third rank, there is a phosphate buffer. Remember, this sequence is from the most effective buffer to the least effective buffer. So sequence over here is important. And similarly, I had also shown in the blood, intracellular fluid and urine. In case of blood, it is almost similar to extracellular fluid. Here again, the most effective buffer is the bicarbonate buffer and the least effective buffer is the phosphate buffer. You can see in the extracellular fluid, the most effective is the bicarbonate and least effective is the phosphate. On the middle rank, there is a proteins as a buffer in extracellular fluid. In case of blood, the situation is same. See, the middle rank, it is of the protein. But we know that in the blood, hemoglobin is richly found, right? So here hemoglobin is given the second rank and in all other proteins that are known as plasma protein inside the blood, that is given the third rank, right? So ECF and blood practically both are same as far as buffers are concerned. In case of intracellular fluid, phosphate buffer becomes the most effective buffer and on the second rank there is a protein buffer. And in case of urine, we have two buffers, that is ammonia and phosphate buffer. We need to discuss all of these buffers, but these urine buffers, they are somewhat unique. So I will discuss these urine buffers along with the renal regulation of pH, right? So here in this remaining video, I will discuss about bicarbonate buffer, then protein buffer and then phosphate buffer. While discussing about the protein buffer, I will specify some of the properties of hemoglobin buffer which is extra effective, right? So by discussing these three buffer, we can cover ECF, blood and intracellular fluid. And as told you, urine buffer will be discussed along with the renal system of regulation of pH. So let's first start with the bicarbonate buffer. Here bicarbonate buffer system, it is consist of weak acid, that is carbonic acid, and bicarbonate ion, that is conjugate base, right? So this carbonic acid is partially dissociated into H plus and bicarbonate ion. Now this square, it indicates a bicarbonate buffer system. Here for the clarity of diagram, I had not shown you this carbonic acid, rather only H plus and bicarbonate ions are shown in this, right? And just for an example, I had taken 4 H plus ions and 4 bicarbonate ions, right? So initially we have a 4 H plus ions as we are more interested in to the hydrogen ion concentration. Now let us see what will happen when strong acid is added to the system. Remember, acid is represented by Ha, and as it is a strong acid, it gets completely dissociated. So in this side, I had given the example of dissociation. So Ha here it is strong acid which is getting completely dissociated into H plus and A minus. So when such strong acid is added into this system, there will be appearance of extra H plus and extra A minus. Here I had again not shown you A minus ions, rather only H plus ions are shown. So suppose 3 H plus ions are added because of addition of this strong acid. So now we have initial 4 H plus this 3 extra H plus ions which is added by this strong acid. So here you can see that total 7 H plus is there. So there is an apparent increase in the hydrogen ion concentration. What will happen if the hydrogen ion concentration is increased? This equilibrium will get disturbed. So as the concentration of hydrogen ion is increased, this equilibrium will move towards the left side. So which is shown by this bigger left side arrow and smaller right side arrow. So what will happen? H plus will start combining with bicarbonate ion. So as you can see, H plus is combining with the bicarbonate ion and it is converted to H2CO3, right? So now we see that we have only 5 H plus left. So again summary, initially 4 H plus were there. By adding a 3 strong acid, we are getting 4 plus 3 H plus, that is total 7 H plus. But thanks to this bicarbonate system, we are ending up with only 5 H plus. So that means if buffer would not have been present, it would have been 7 H plus. But rather because of the buffer, it is only increased by this 1, that is making total of 5 H plus. So we can say that bicarbonate buffer is resisting the change in hydrogen ion concentration, and so it is resisting changes in the pH. It cannot completely stop change in the pH, but it decreases the magnitude of changes in the pH. Now let's look what will happen when the strong base is added, and general representation of strong base is AOH. Again this square indicates bicarbonate buffer system, and here 4 H plus and 4 bicarbonates are shown. So strong base gets completely dissociated into OH minus and A plus. So let's add this extra OH minus ion into this bicarbonate buffer system. Here again for the clarity of diagram, A plus is not shown, and here I am assuming that 2 molecules of OH is added, right? So this 2 OH minus ion will appear. Now what will happen? This OH minus, it starts binding with this H plus. So initially we have 4 H plus, right? And as this OH minus ion, it binds with this H plus, what will happen? It is converted to water and we are ending up with only 2 H plus. So this addition of strong base is decreasing the hydrogen ion concentration, right? But here we have bicarbonate buffer system. So see what happened is that hydrogen ion concentration is decreased by the addition of strong base. But as hydrogen ion concentration is decreased, this equilibrium, it is getting disturbed. So now more and more carbonic acid will move towards this side, that is dissociate into H plus and HCO3 minus. So this net reaction will move to the right side, which is shown in this arrow, which is shown in this reaction by this bigger right side arrow and smaller left side arrow, right? So in this system, some extra H plus and some extra bicarbonate ions appear, right? So now you can see that we have again 4 H plus, right? So here bicarbonate buffer system had registered the change in the pH. So by this we understand that bicarbonate buffer system will register the change in pH whenever any strong acid or strong base is added to the system, and similar mechanism occurs along with all the other types of buffer. Now let's check certain facts about the bicarbonate buffer. As mentioned earlier, bicarbonate buffer's pKa value is 6.1, and we know that buffering capacity is maximum within a range of pKa plus or minus 1. So in this case, in case of bicarbonate buffer, the maximum buffering capacity is between 5.1 to 7.1. Whereas if you look at the pH of ECF and blood, it is 7.4. This 7.4 is the outside the range of this buffer, bicarbonate buffer. But in the earlier slide, we had seen that in case of ECF and blood, the most effective buffer is the bicarbonate buffer. So theory is different. Theory is telling you different story, and practically you are observing something different. So one natural question arises, that is, why bicarbonate buffer is the major buffer in ECF and blood, whereas theoretically speaking, it should not be major buffer. Then what is the reason? So there are total two reasons for this. Let's look at the first reason. That is, in blood and ECF, the ratio of bicarbonate ion to carbonic acid is 20:1. Now you may ask, so what will happen if the ratio is 20:1? How it will justify that bicarbonate buffer is the major buffer of ECF or blood, right? So we have Henderson-Hasselbalch equation, right? pH is equal to pK plus log of bicarbonate, that is conjugate base, divided by carbonic acid, that is acid, right? Now we have a value of all these parameters. So pK is 6.1 and this ratio, it is 20:1. So 6.1 plus log of 20 divided by 1, and we solve it, then we get an answer of 7.4, which is exactly the pH of extracellular fluid and blood, right? So now we know the importance of this ratio. Because of this ratio, the bicarbonate buffer system becomes a most effective buffer system of the plasma, ECF or blood. Now you might be curious that what are the actual value of bicarbonate? What is the actual value of H2CO3 in blood? So for your reference, plasma bicarbonate is the 24 milliequivalent per liter. Carbonic acid, its value is 1.2 milliequivalent per liter. And if you find out if you do the ratio, you will get 20:1. Now I had given you one specific value, but whenever we consider biological system, it is not a single value, it is always a reference range. So in case of plasma bicarbonate, the reference range is between 22 to 26 milliequivalent per liter. Whereas in case of this carbonic acid, it is between 1 to 1.4 milliequivalent per liter. Here one more important thing is that most of the clinical laboratories, they do not measure this arterial carbonic acid. Instead, another parameter is measured, that is partial pressure of arterial carbon dioxide. This small a indicates it is of the arterial blood, and its reference value, its normal value is the 40 millimeters of mercury. Again, its reference range is between 35 to 45 millimeters of mercury. So this from this PaCO2, partial pressure of arterial carbon dioxide, this arterial carbonic acid concentration can be calculated. How it is calculated? So the formula to convert this partial pressure of carbon dioxide to carbonic acid is this, that is the concentration of carbonic acid is equal to partial pressure of arterial carbon dioxide into solubility coefficient, and the solubility coefficient of this carbon dioxide is 0.03. So in this Henderson-Hasselbalch equation, instead of this H2CO3, we can also put up this value. So your Henderson-Hasselbalch equation looks like this. So here I had discussed the first reason that why bicarbonate buffer is the major buffer of extracellular fluid and blood. The second reason is that bicarbonate buffer system is the open system. Now, what is the meaning of open buffer system and why it is the reason for major buffer of ECF and blood, right? So see, this is the bicarbonate buffer system where this is the weak acid and this is the conjugate base. This H2CO3, it can be synthesized from the carbon dioxide which is dissolved in water and by the action of this carbonic anhydrase. Now, in this buffer system, this particular carbon dioxide and this particular bicarbonate, they can be added to this system or can be removed from the system. If you look at the carbon dioxide, it can be added to the system or removed from the system by this respiratory mechanism or lungs. Whereas this bicarbonate, it can be added to the system or it can be removed from the system by the renal system, right. So this buffer, its various component, they are in continuous exchange with other body system, right. So their components are not constant, they are always manipulated by some other organ system, and that's why we can call this as a open system. In case of closed system, this component cannot be exchanged. For example, all other buffer mechanism of human body, that is phosphate buffer, protein buffer, ammonia buffer, they are not with the constant exchange. So they are considered as a closed buffer system. Whereas bicarbonate buffer, it is the open buffer system. So these two reasons justify that bicarbonate buffer is the major buffer of extracellular fluid and blood. Now next, we'll look at the phosphate buffer. What are the components of phosphate buffer? So weak acid, it is H2PO4 minus 1 and its conjugate base is HPO4 minus 2. Here the phosphate buffer, its pK value is 6.8, right? And as we know that maximum buffering capacity falls between pK plus or minus 1. So here maximum buffering capacity will be from 5.8 to 7.8 pH. And we know that the extracellular fluid and blood, its pH is 7.4, and this is very well falling within this range. But we had also seen that phosphate buffer, in reality phosphate buffer is the least important buffer system for the blood and ECF, right? So question arises that why phosphate buffer is not major buffer of ECF and blood, whereas theoretically looking, it seems that this should be the major buffer system, right? So there is a reason for this, that concentration of this phosphate buffer is very low in blood, and that's why it is not effective, right? Earlier we had seen that buffering capacity, it is dependent on concentration also, and here concentration is not proper, it is very low. Whereas we had also seen that phosphate buffer is major buffer in case of intracellular fluid and in renal system also. So here what happens, their concentration is higher, right? So however, intracellular fluid and renal tubules are rich in phosphate, so it is a major buffer at this place. So this was a simpler one. The last buffer system that I need to discuss is the protein buffer. Remember, protein, it is the chain of amino acid, and all the amino acids are joined by peptide bond. And this amino acid chain can be quite longer. But to understand protein as a buffer, I am taking example of polypeptide chain of 4 amino acid residue. So this is the polypeptide chain of 4 amino acid residues. Now for you to clearly understand, I am demarcating the lines showing a separate amino acid, right? Now in case of any amino acid, there are at least 2 ionizable groups, and these ionizable groups are responsible for the buffering. But the problem with the protein is that peptide bonds are made up between carboxylic group and amino group, right? So almost all the amino acids, all these 2 ionizable groups are participating in the peptide bonds, so they are not ionizable except for this N-terminal amino group and this C-terminal carboxyl group. So out of this peptide chain, only one alpha amino group is present, which is in ionizable state, and only one alpha carboxylic group is in its ionizable state, right? So if we examine their pK value, the alpha amino group of the N-terminal, its pK value is 8, which is covering a physiological range, and alpha carboxylic acid group, its pK value is 3.1, which is outside of the physiological range. So this is not important for the buffering, only this one is important for the buffering, right? Now apart from these 2 ionizable group, some amino acid has a ionizable side chain, which is shown in this diagram by this R1, R2, R3 and R4. So we have total 20 amino acid, and out of this 20 amino acid, only 7 amino acids are such that their side chain is ionizable. What are these amino acids? So these amino acids are lysine, arginine, histidine, aspartic acid, glutamic acid, cysteine and tyrosine. And all their respective pK values are given. And if you examine closely, only cysteine's pK value is falling within the physiological range. And somewhat nearer is the histidine, whose pK value is 6. Remember, these pK values are of the side chain R group. Okay. So, in case of any polypeptide chain, there are total 3 functional or ionizable group can be there, which can be helpful in the maintenance of pH. One is N-terminal amino group. Of course, this carboxylic group is not useful. Then side chain of histidine and side chain of cysteine. Only 3 types of ionizable groups can be seen. Now, again the question that histidine per se, it does not cover exact pH range. See, its pK is 6, so its effective range is from 5 to 7. It is not covering 7.4. But as we had seen just in case of bicarbonate, that their concentration is higher and they have a proper ratio, almost similarly looking concept can be applied to the histidine. Generally, our proteins, they are rich in histidine, right? So here histidine becomes more important than the cysteine for the maintenance of pH. If you talk about hemoglobin, it has total 38 histidine molecules and 6 cysteine amino acid residues, right? So hemoglobin, as it is very rich in histidine and cysteine, it becomes one of the very important buffer in case of our blood. So that's all for today's lecture. In the next video, I will discuss about the respiratory regulation of pH. If you have any query or confusion, please write it down in the comment section below. Thank you.